Okay, good morning. Welcome to
KidMath145a.
Hold step away from the board just a little bit. Get rid of that shadow. So you've been a little bit sick lately, right?
Yeah.
So we're going to have a fun talk today where we just talk about exponentials and logarithms, but just for fun. Not super serious. Just give you a little background. Okay?
Yeah.
Okay. All right. So in the last section, like last week when we were talking about compound interest, we talked about sort of compound... Sorry, my pen's not so good here. Compound annual would be like 1 plus 10% to the first power. And then semi-annually was 1 plus 10% over 2 squared. And we got all the way down to 1 plus 10% over n to the nth power as n went to infinity.
Yeah.
And this looked like the number e showed up, right? This turned into e to the 1.1. And the surprising thing was e showing up, number one. And number two, that when we got larger and larger and larger numbers that we were compounding, the numbers themselves didn't get larger and larger and larger, right? Do you remember that?
Yeah.
Okay. So when we talk about compound interest, the number e shows up. And the inverse function of exponentials are logarithms. And logarithms are very commonly expressed not in base 10, like we've been talking about, like log base 10 of 100 is what?
It's 2.
2. That means 10 squared is 100. But the most common expression of logarithms, you grab that marker over there, is actually in base e, funny enough. And it has a special number, or a special symbol, log base e of x, we write as ln of x. Okay, so you're going to see later on in math ln of x a lot. And it comes up in some really surprising places, and I just wanted to show you 3 different ones today. Okay, so that'll be A, B, and C. The first place where ln comes up, which is really surprising, if you look at this graph of y equals 1 over x, okay, so I'll put 1 here, 1, and then so at 2, where is 1 over x when x equals 2?
It's a half.
Half. Where is 1 over x when x equals 3?
A third.
How about when x equals a half?
It's at 2.
It's at 2. Okay, we look at this graph y equals 1 over x, and we look at the area under this graph, this funny shape that sort of looks like almost like an infinitely long triangle that goes from 1 to 0, but it only goes down to 0 to infinity. See that? If we stop at any point x here, the area from 1 to x is ln of x. So somehow e to the x has to do with these, with the area under this curve. And there's one really surprising thing about this. If you look at this area, you can try to build it by rectangles. Build a rectangle like that, 1 high, 1 long, 1 half high, 1 long, a third high, 1 long, and you get 1 plus a half plus a third plus a fourth. And that's bigger than the area under the curve, right? You see how it's above?
Yeah.
Okay. But the area under the curve is a logarithm function that goes to infinity. That must mean the inverse integers don't converge. They add up to infinity. That's pretty surprising, right? Because they get super small.
Yeah.
Okay? And I've already showed you before, I don't know if you remember or not. Do you remember what the inverse squares add up to?
No.
These add up to pi squared over 6. So the inverse squares actually converge. So the inverse integers add up to infinity, and we can understand, one of the ways we can understand that is the relationship with logarithms. So this is a pretty surprising fact that you get infinite. Because like I said, the numbers get really small, right? Okay, let's talk about 2 other things. Okay?
All right.